we want to talk about a very important notion in manifold theory called transversality. In this video, we're gonna give some motivation for this notion. Now, there are two ways to motivate this. We can think of this as a generalization of regular value, or we can motivate this via certain needs for building intersection theory. So let's start with this regular value angle. Recall that when we were talking about submanifold, we had a natural question, which is that given a smooth map from M to N, when is a fiber of F a regular submanifold of M? Remember, then the regular level set theorem tells us that if Q is a regular value of F, then the fiber over Q is going to be a regular submanifold of M. We have used this to show, for example, that the unit sphere is a regular submanifold of R3. Now we want to ask a more general question. We want to look at fiber not just of a point. Now we want to actually look at fiber over a submanifold of N. We can then ask, for which submanifold Z of N is the fiber F inverse Z going to be a regular submanifold of M? It turns out that a good notion to capture this is transversality. So we'll define transversality in such a way that if Z is transverse to F, then the fiber over Z is going to be a regular submanifold of M. And this will be a true generalization of regular value in the sense that Q is a regular value of F if and only if Q is actually transverse to F. So that's one way we can motivate the notion of transversality. Now another way we can motivate this concept is via intersection theory. If we have two submanifolds Z and M of submanifold N of complementary dimension, then they intersect each other in a set of dimension 0. If one of them is compact, then the intersection will consist of a finite number of points. We are interested in defining maybe some kind of intersection numbers that counts the point in this intersection. We don't want to just define this intersection number to be the number of points in the intersection, because for example, let's look at these two pictures. Right, in both of these cases, the intersection consists of just one point, but the local geometry here are very different. So we want this intersection number to capture multiplicity. Thus, we want some terminology to distinguish intersection. Right, this kind of intersection has multiplicity, but this and this do not have any multiplicity. These types of intersection, when there are no multiplicity, these are called transverse intersection. Thus, we want to define some notion of transversality to capture this kind of picture so that we can say that M is transverse to Z if their intersection looks like this. Now, you might feel a bit confused here because this transversality seems to have nothing to do with this transversality, because here this notion is about transversality with respect to a map, whereas here we are talking about two submanifolds being transversal. So what's the relationship here? Well, by definition, M and Z are transversal if and only if Z is transversal to the inclusion map from M into N. I just noticed here that I wrote transverse instead of transversal. It should be transversal. Sorry, I'm really too lazy to re-record this video. Alright, so those are two ways we can motivate the definition of transversality. Next up, we're gonna give a formal definition.